Any questions?
Can you go over what you left us with on the last,
David?
can you go over what you left us with on the last, question?
The problems we're working home?
Yes.
What was the setup?
It was, 3 kilogram mass moving 4 meters a second to the right. 1 kilogram mass moving 6 meters a second to the left.
And which technique did you want me to use?
The third one.
Okay. All right, so dealing with a perfectly elastic collision. And, Kelly.
Yep.
I believe these are yours. I can take them. All right, perfectly elastic collision using the third technique. So first thing we need to do is figure out the center of mass frame or the zero momentum frame. You can do it two different ways. To me, the simpler way is to solve the perfectly inelastic collision problem first. In other words, afterwards, they're going to stick together and travel in some direction at some speed. So my total momentum initially is 12 plus negative 6. Dramatic pause for people who have questions about how I got those numbers. And so, which is equal to 6. I now know my total momentum after the collision. 6. And so 6 is equal to, I've got 4 kilograms that have stuck together. This is a 4 kilogram mass. So it's equal to 4 times whatever that final velocity is. And so my final velocity is 1.5 meters per second. Alternatively, doing the exact same problem, to find the zero momentum frame, I do 3 times 4 minus v, where v is going to be how much I'm going to shift everything, plus 1 times negative 6 minus v is equal to 0. So basically doing mass times velocity after I shifted into the zero momentum frame. So this is 12 minus 3v plus negative 6 minus v equals 0. Combining things, I get 6 minus 4v equals 0, or 6 equals 4v, v equals 1.5. So it gets to the same place when you solve it more generically or just solve the perfectly inelastic collision problem. Now we shift. So this is going to be my 3 kilogram mass and my 1 kilogram mass. So first, my velocities in the problem frame, or what I'll just call the lab frame. So that's 4 and negative 1. I shift to zero momentum. So I subtract 1.5. So this is the velocity in the zero momentum frame. Something's off here. 4, negative 1, subtracted 1.5, negative 2.5, 2.
Can it be negative 6?
Yeah, thank you. Negative 6. So negative 7.5. Thank you. Then there's the collision. And I need my total momentum to be 0, and I need my kinetic energy to stay the same. Well, kinetic energy stays the same. That means I have the same speeds in this frame. And my momentum stays 0 if I just multiply everything by negative 1. So I get negative 2.5 times plus positive 7.5. And then I shift to lab frame. So I subtracted 1.5 before, I add 1.5 to get out of it. And end up with -1 and 9. So V3 final is -1 meter per second, and V1 final is 9 meters per second.
Why do you subtract by 1.5?
In this technique, I'm trying to get into the zero momentum frame. And so we figured out that the center of mass is traveling at 1.5 meters per second. And so I subtract by whatever it takes to get me into that frame. In essence, as an observer, if those are the velocities measured by someone just standing here, as an observer, I'm now going to move 1.5 meters per second in this direction in order, and it's going to change the velocities that I'm observing. Questions? And again, this is just one of the 3 techniques that we talked about. That's not the one that you have to use. It's just Ethan asked, and this is the method he wanted.
What does it say next to it? Said V lab? This one of the, yeah.
There, V lab.
Oh, it does say V lab?
Yeah, I'm reviewing this as sort of the lab frame. It's the observation. We're watching this thing happen.
So V
I
total.
would have written, it's the problem frame actually, but the lab is shorter. I cut you off, I think.
Like V total, is that what we're?
It's the velocity, because how fast something is going depends upon your frame of reference. Like, we're going 0 meters per second, or for cars zipping by, we're going at, well, at that point on the road, 50 miles per hour. Or if you think about it, we're on the surface of the Earth and the Earth is turning. So it all depends upon your viewpoint. And so the first one is the viewpoint that told us those were the velocities, whatever you want to call it. Other questions? And then other questions on this or anything else? I think all of you know what goes up downstairs, alone or in pairs.
It's 19.
Now, it's not ideal. If this were an ideal spring, then it would not interfere with itself, as it did just then. It would oscillate in what's known as simple harmonic motion. It comes to actually pretty darn close to simple harmonic motion, good enough for what we're doing. So what I want to talk about now is simple harmonic motion. All right, motion it's moving. Should not be a shock. Harmonic means that it is repetitive motion. Usually can be expressed by a sine or a cosine to describe it. And simple, we're talking about friction-free, no heat generated, the thing will go on forever. So, no stopping on its own. Sine or a cosine, and then motion moving. I mean, I could express that as a cosine with an amplitude of 0, but not really in motion though. All right, so if I plotted position versus time, as it's oscillating up and down, if I just sort of map that, it would kind of look like that, where the height is how far up it goes, the position of the bottom of that spring versus time. So just call this position versus time. So let's get some vocab down. Amplitude. Well, I'm sure someone in here's had it. What's an amplitude?
Height of the wave
From where to where?
from,
Its lowest point to its highest point. From its lowest point to its highest point.
That would actually be twice the amplitude.
The origin. Like, like the X, yeah,
Midpoint.
midpoint, sorry.
All right, so there's my amplitude right there, which I'll just generically label as an A. The actual letter would depend on what kind of wave we're talking about. Period. What's a period? So, for those just tuning in, amplitude. Put distance in quotation marks because it's not necessarily physically a distance. Now, in this case right here, if this is oscillating up and down, it would be a distance. But if I'm referring to sound, the amplitude could be dealing with the pressure of the sound of the wave that hits you, or it could be dealing with decibels and or loudness and so forth. So distance in quotation marks from central line to peak or to drop. If it's indeed simple harmonic motion, those would be the same distance. All right. Period. Someone was about to tell me.
the distance between periods, between peaks.
I'm gonna go no. Now, if I had you draw up here what's the period, I think you would draw it correctly, but the wording was off.
The time it takes to get from one point to the same point? Like,
Yes.
As simple
What was different from what he said?
time.
Yes, it is a time. Period indeed is a time, so it would be the time difference between any point on a wave to the corresponding point on the wave. So from there, from peak to peak is usually the simplest one, since that's a time axis. If I did it from here, it would be to here. And if drawn properly, those times differences would be the same. The capital T is the symbol for period, and this is why I don't use capital T for tension. Period, and it is the time to create one wave, or in general, I guess that's specific to wave creation. In general, period is time to create one cycle of repetitive motion. Now, the units of amplitude depends upon the situation, but period does have particular units. What are the SI units of period? Standard units of period.
Seconds.
It is indeed seconds. It's a time, so it is seconds. Now, I wrote seconds down there, and that's traditionally the way it's done. It's really seconds per cycle. But per cycle is usually not written. If I flip that over and I look at cycles per second, cycles per second is a unit of what?
Speed.
Radians.
Not radians.
Frequency?
Frequency. And a cycle per second is usually also known by a different word.
Hertz?
Hertz, capital H, lowercase c. Named after? Yeah. There are only a couple of units that aren't the person's full name. The Farad, named after Faraday. So from this, and so if time is the seconds per cycle and frequency is cycles per second, in other words, it's how frequently is this wave going on, I mean, how many of these waves do I get per second? That the period is just the reciprocal of the frequency. And in one of the videos, I talk about another symbol for frequency. This is good for now, but as you watch the videos, you'll recognize that there's another symbol that sometimes gets used. All right. Wavelength. The symbol for wavelength that I will be using is the lambda. What is the wavelength?
The difference between top of the wave, top of the wave.
Be more specific.
Time between,
No, not time.
space between wave to wave.
Yeah, or the
Crest.
distance. This is, Luis was just ahead of his time. So the wavelength, in essence, it's how far a wave travels in a period. So, and that is the word far there. Just like the way it looks. Far, there we go. What would be the standard units of wavelength?
Meters?
Yes. It is a length. Meters per cycle, probably more officially, but the per cycle is usually not written. All right, so if I have a wave that's being produced here, I pull this down, let go, the thing's gonna oscillate back and forth. I can find the period just by doing a timing. So let's go ahead and do that. If someone has a stopwatch on their phone or whatever, we just need a rough number right here. So I got a couple people. All right, I'm gonna do 3, 2, 1, go. When I say go, I'm gonna let go. Probably easier if I go up here. Okay, 3, 2, 1, go. 2, 3, 4, 5, 6, 8, 9, stop.
6.8.
You got the same thing?
6.83. 6.83, same thing, almost.
6.64.
Anyone else? So the average of those was a 6 point, did?
It was 6.88.
8. Ah, okay. So doing the fancy math here, so I got 4, and 23 is 27, and 28,
6.783.
6.783.
Yeah.
That's for 10 oscillations, and so if I divide by 10, I end up with a period of 0.6783 seconds. So my frequency, how would I find my frequency?
Inverse.
So 1 over the 0.6783. Somewhere around 1.6, but what do we get? No, closer to 1.5.
1.474.
1.5. Units?
Hertz.
So I've got this frequency of almost 1.5 hertz there. If it's truly simple harmonic motion, I should be able to express it as a sine or a cosine curve. Well, let's think about that a little bit more. There's an implied mass of the spring, but let's assume that it is massless spring. I attach a mass to it. In theory, I attach a mass to it. It's going to get pulled down a certain amount. So let's just